Okay. Hey, Mark. Let's. So basically, yeah, this is about. This is a paper that I started, I guess, 2 years ago. And the basic idea is my background is I have a pure math PhD. Been interested in category theory for a long time and type theory, but I want to do stuff that has real world applications. And I think functional programming is a very elegant way of reasoning and doing and organizing code. And the problem is it doesn't seem particularly useful right now. I don't think it's found its killer application. And this is one potential application which I think has some promise to it. So let me just talk a little bit about what a hybrid system.
So actually, but before you get started, I just want to call out to people watching that. So I first met Paul like a year ago from a Hacker News thread where he seemed to be the only other person I knew interested in applying category theory to robotics. He said he was working on something, and then a year later he actually pulled through and sent me like a long and like meaty looking paper with some slides. So this session is mostly us going through that work and him explaining to me the basics. So it's something I've been looking forward to for a while, and I'm really happy it came through. So yeah, so Paul, just go for it.
No. It's great to hear from people who are interested in your work, even if it's a little bit off the deep end. Well, it's a little bit mathematical, but hopefully I'll get a applications paper out pretty soon, which will apply a lot of this stuff to some physical system. So Dan Koditschek, oops, let me just do it like that. Yeah, Dan Koditschek is a robotics. He's in charge of a robotics lab at Penn, and he developed some. Maybe Minitaur. If you're a robotics person, you might have heard of Minitaur, which is this. Why don't I just?
Just show it to us, yeah.
Yeah, Minitaur, Ghost Robotics. So Ghost Robotics was basically a startup that spinned out of Dan Koditschek's lab, and hopefully this won't. Oh, contact not supported. Maybe I have to.
So I think you also had the video in your slide deck, if I'm not mistaken.
Yeah. So you guys can you can click on this. I could probably just, do you think it's worth sharing it? I can just go to the Mac and I'm sure I can share it directly from the Mac. Why don't I do that?
Go for it. Go for it.
Okay, so stop share.
Yeah, so funny story, I actually applied to Ghost Robotics, but they gave me a programming interview that was really dense on embedded programming. So I was never able to actually finish it. But it's a company that I've been following for a while, yeah.
Oh, that's cool. Yeah, I'd never heard of them until I joined this project. And then like Avik, do you know Avik by any chance? Avik is one of the co-founders and Gavin, I guess, is the CEO.
So the guy I met was Tom Jacobs. I think he's the head of software, if I'm not mistaken.
Yeah.
He's also very active on Twitter.
I don't think anything. Yeah. I haven't met him. I have an office. I think, I don't know if they moved out yet, but I had an office that was in they were doing stuff there. I had to email him one time for a software license, but that's it. Gotcha. Okay, so let's just do Ghost Robotics. Minitaur. Okay. So yeah, I guess they have a ton of these videos.
Hi,
oh my
I'm Rick
gosh.
Hefner, Program Director at Caltech, and I'm here to introduce you to the post.
All right. Yeah. So this is their little robot that jumps. You know, it's a direct drive robot. Can do a lot of tricks. And one of the things that they're thinking about, or that Dan Koditschek's been thinking about for a long time, is how to do composition. So that means transition. So suppose you have two different behaviors, like climbing, for example, or walking and jumping, and how can you have a formal basis for transitioning between them rather than hard coding it. And other things like parallel compositions, meaning, suppose you can control 1 foot, or you can have you can have a hopping controller for a single foot, and you want to combine them into a gate. That's kind of a fancy example of a parallel composition.
That's
And then
interesting.
there's hierarchical stuff.
So,
So
so
yeah,
question
I'll
there.
get into that in a little bit later.
So it sounds like
And then there's also stuff. Let me see if they have a Jerboa picture. So a little bit simpler. Maybe pen Jerboa.
Yeah, so it sounds like you're talking about two main forms of composition. One is like the sort of flow-based, where it's like action 1 followed by action 2 followed by action 3. And then the other is like combined submodules to do a more complicated task. So that's what you mean by parallel versus sequential?
Yeah, sequential is like do one task, then do another task. Go do one task until you're in like an appropriately guard, you're in a condition under which you can apply a controller that performs a second task. So do one task, then do another task. And then parallel composition means you're doing two things at the same time, perhaps in some interrelated way, but in like the simplest case, you're just doing them independently.
And just as a sort of but is parallel composition in general harder? Because that sounds kind of harder to me, right?
Yeah. I mean, I would say they're pretty different in nature. But yeah, they're pretty different. It depends on what exactly you're like. If you're doing independent parallel composition, like a lot sometimes. So one of Avic's early papers was about basically conditions under which you could treat a robot, like say the Minitaur robot, or like I think it was a two-dimensional situation. You could do a parallel. So you have two legs, and you want to put them in like a pronking gait, which means they jump at the same time, like like that, or what's the other, back and forth. I forget what that's called, but there's two of these gaits, and you want to so you'd want to do a parallel composition of the single leg hopping behaviors, and under certain conditions you can actually you can do that, and there's some theory you can actually treat them independently depending on like the moment of inertia of the rigid body between them. So there's different. I mean, it's a hard problem, but there's different things you can do.
But sort of like the applied benefit of this is that one, your controller code is simpler. It's working over a smaller state space as opposed to like a product of two things. It's working over one thing.
Yeah. That's
simpler,
exactly
easier
it.
to debug. It's modular. So there's all sorts of benefits, I guess, that like, and I guess like one thing that this gets into, like in reinforcement learning, for example, like one of the main challenges is like sample efficiency. Like the fact that your state is so big, it's really hard to make anything converge. But if you make your state so small by making it independent, the sum of many small problems is a lot easier than the product of a bunch of small problems.
Yeah,
so,
yeah. I mean,
I like that.
I mean, if you want to do real legitimate transfer learning, right? Like if you actually want AGI or something, you can't. There's going to have to be some composition involved. But yeah. As far as reinforcement learning goes, I actually. Oh, yeah. Sorry. I also do some contracting for the Air Force, and so we're doing some reinforcement learning there. We're also thinking about like compositional things, ways of applying like similar compositional ideas. But yeah, it's obviously pretty hard to do it. I mean, in either case, but reinforcement learning especially, right? But
interesting.
Yeah. Okay. So what was I going to say? Oh yeah. Oh, there is a little bit of code. Let me just since you mentioned some of it's closed source, but I do. Oh, let me just advertise this one little thing because I think I did upload some a little bit of code which make okay. So this is I don't want to. Yeah. So there is like basically the paper. I coded a little bit of the stuff that was in the paper. Right now, I won't get into this right now, but there's like an idea of a fully abstract parallel so if you have a hybrid system data type or a class in C++ terms, right? There are ways. Oh, sorry, this is a mode, but yeah, you can do like there's different. You could in the ideal setting, you would be able to do like this parallel composition, sequential composition, and so on. Yeah.
And so sort of just like a high level question here, like one, I found it interesting that you're sharing C++ code, so do you think that ultimately seeing category theory applied will look like more like for robotics, it'll be used category theory ideas in C++ versus in Python, versus for machine learning, use it in Python. And you think like Haskell is more of an experimentation language? Like why isn't this Haskell code, for
Well, it's
example?
actually, so the reason I did it in C++ is because if you look at one leg of, it's because Gazebo and Ross, right? So they have a simulation model of a Minitaur leg in Gazebo, which Gazebo and Ross or whatever, and you can see it in hopping Gazebo. And so the reason I wrote this up was because I wanted to refactor their existing code, which was basically a big event loop with a bunch of modes. So the way, yeah, maybe I can talk a little bit about what a hybrid system is before I get into it. But
Yeah, go for it.
I wanted to refactor it to use some more functional ideas.
No, but that's interesting. Like you're thinking of a real environment. Like you're saying, okay, well, what's the simulator people use? It's Gazebo and Ross. Well, I need to make my ideas work there, or else they're not very useful. I think that's
yeah. That's
the right way
exactly
to go.
right. I mean, the thing is about functional programming is you can like if you have a Turing complete language, you can do whatever you want, right? But there are language features that are really useful for doing and make that are useful in general. That stuff like Haskell. Haskell is great for doing. I prefer to code in Haskell if possible, but there's a lot of different constraints that you have to deal with. Okay, so let me switch back to the. Actually, why don't I? Yeah, maybe I'll switch back to the iPad really quickly,
Go for it, yeah.
and then I can give some example stuff. So share screen again. Yeah, this is my first time using the full-fledged Mac plus iPad combination. So
I mean, like I think this is sort of going to be the talk format of the future because like it's a lot better than just a deck like you're showing us. It's sort of like a better better window into your brain than a PowerPoint, I think.
yeah, like Amazon, right? I think they're pretty against PowerPoints. Like what they do is you have to give everyone a narrative before you send everyone a narrative by the beginning of a meeting, right? Like a little paper, a page or two or something, and then they have to read it. Everyone sits down in the meeting and reads it together.
Yeah. I honestly think it's not entirely insane just because so when like I worked at a big company when I was at Microsoft, and I often felt like people waited for meetings to do the work. And I often feel like, well, you should do it beforehand and then come in the meeting to discuss it. I always found this idea of a meeting as a sort of way to solve procrastination to be just like a very roundabout solution.
Yeah. Well, I mean, the thing is, motivation is really social, right? So
Yeah.
it's like maybe the point of the meeting, maybe that is the optimal thing the optimal reason for meetings is to get rid of procrastination.
Yeah, I agree. So I add some
Okay.
social pressure.
Okay, screen share. All right. I wish there was it would be awesome if you could kind of
do it like with one button or something. Like
yeah. Okay, come on, please. All right, there we go. All right, so yeah. Also, it would be if the mouse and the touch was better integrated, that would be even better. Okay, so let me talk a little bit about what a hybrid system is, or hybrid systems, or starting from robots. So let's say I have a single leg, jumping robot. So basically you have here's the ground, here's like some mass, and so this is a leg of a robot, and here's a foot, and you can model this as this is some spring, and you have a mass on top, and you can control. So you can do control by, for example, changing the spring constant. That's one way of doing it. Oops.
so this is like programmatic springs, right? Like in the real world, this would be a spring where you just literally have an API where you change the spring constant in this case.
Yeah. So I guess I'm not an expert in this programming stuff, but this would be like this would be an interface, or what they call as a template for an actual leg, right? And so the actual leg would involve like a bunch of actuators and stuff. But what you can do is you can translate, like you can treat an idealized leg as being this spring, what's it called? Spring loaded inverted pendulum, right? Maybe if you want to Google it, SLIP. So you can program it using the template, and then if you've set it up right, then the actuator that you can actuate in a way that it does emulate the template, right? And so it actually works out. Okay, so let's talk about like the simplest possible, like a hopping gate. Oops. So a hopping gate, what that means is you have your little spring, and here, let's say it's in the air at the beginning. So it corresponds to let's say 3 modes. So maybe, sorry, you have, let's say, aerial mode, or flight. Maybe flight is a better word. So you have flight, and then you hit the ground, and let's say that's compression, and then you have a decompression.
You know what's fascinating about you drawing this image is it looks very similar to the way animation state machines are set up in game engines.
Yeah.
Where like it's like, well, like once you're in flight, trigger this animation, then wait this long, and then trigger compression, then wait, and then there's some events that would be responsible for the transition. So this is actually very familiar, like this kind of picture, I would argue, to a lot of game developers already.
Cool. Yeah, that's great. Yeah, it's kind of it's a state machine picture, as you mentioned, and it's kind of like a universal idea. And yeah, so this is kind of the mode or the discrete structure. So this would be like the graph of a hybrid system. So this would be the graph that would correspond to a hybrid system that would be, a controller of a hybrid system. And so you can describe a hopping gate, using this graph. And then the one other element that you have to add is you have to have vector fields, right? So there's stuff. So here, these are called modes. So a hybrid system corresponds to it's hybrid continuous and discrete system. It has modes which correspond to the vertices of the graph, which are like flight, and those are the modes. Hopefully I haven't made this too legible. Flight, decompression, and decompression. And you have a graph that corresponds to allowable transitions in the modes, right? So this edge here corresponds to hitting the ground. So maybe I'll, so this is like ground impact or something. And this is, this is kind of the bottom of, maybe bottom apex, I'll call it. And this is liftoff. Okay, and so you have these modes, and these are called reset maps. So, oh my gosh.
So reset maps are the arrows in this case?
Yeah, the reset map, or let me just call them resets. So reset corresponds to a discrete train. So this arrow is called a reset. Maybe I should move this to a different page. See if I can do this. All right. Cut. Oh no. Paste. All right, there we go. Right. So the reset maps correspond to the edges. So okay, so the modes are vertices, e.g., flight, and the resets are the edges. So, for example, hit the ground. Okay, so you have these. So we call this part the discrete. Oh no. Maybe I'll just write it here. Discrete part of the hybrid system. And then at each vertex, oh no, at each vertex you also have, at each vertex you also have continuous dynamics. Continuous dynamics. Okay, so what is a continuous dynamic? What a typical way of modeling continuous dynamics is, as you know, you have a manifold and a vector field. So before people start falling asleep, let's, example. Here's the manifold M. Equals,
so here it's a 2D space, it looks like.
Yeah, R2, right? And you can have a vector field that looks like, let me just draw the axes here. And you can have like this kind of circular type of vector field, right?
So this would be a pendulum, for example, right? Is what you're drawing?
Yeah, exactly. So this has some periodic motion, right? That's the kind of, so this is an example. And if we go back to our, I wonder if there's a better way of adding a new page. Okay, so if we go back to our example, right? So we had, flight. Well, that's an easy one, right? Let's say if we just let's talk a little bit about how you could model this. So remember you have this little spring thing, right? So let's say you have let's say our state space, just for our state space corresponds to, you have like the length of the leg, or not, I don't know exactly what the right way. So length of the spring's extension, spring displacement or something. Let's just call it
let's just L, like that's fine, or D, or whatever you want to call it.
Okay, yeah, sure. Let's say L, and then you have let's say the center of mass. So let's call X center of mass of and let's just say the leg is massless. Okay, so just here's X, and this is right here is L, whatever.
Yeah. So the full system is described with 3 variables in 2D and then 4 variables in 3D in this case.
Right. Or let's do everything. Let's just say everything is. Let's just 2D. Say we're talking about 1D for just for fun. And okay, so what? Let's talk. So flight, obviously, you're gonna have like x double dot equals minus g. So this would be your so you can basically you can define these little, you can define and then compression is going to correspond to well, you have to write down the force equations, but basically you're going to have something like L equals minus K or basically you'll have something like you have minus KL will be maybe divided by some mass. It will be something like your X double dot. This is the kind of stuff that's going on. Okay, so you can define these things, but so all I'm trying to get is this is what it means to be a hybrid system, is that you have both these discrete and continuous dynamics. And the surprising thing is this is a very, as Mark you were mentioning before, this is a very universal thing. Like these kind of ideas would show up. It's a very general way of describing dynamical systems and describing controllers. Okay, so where does the category theory come in? maybe, well, what you want to do is you want to do modular programming with hybrid systems, and to do that, categories are kind of the natural. So let's say, what is the connection between modular programming and category theory? Well, basically the way that category theory comes in is what's called type theory, which is, so type theory, typically if you're working in C or C++ or something, you have some really your types are not going to be that crazy, right? You have, so what is so let's talk about how far should I go? How much do you want to get into the type theory? I guess that's the question.
Like as much as you're interested, and if it goes too much, like, don't worry, I'll steer you, but just do your thing.
Sure. Actually, let me turn on the air conditioner really quickly.
Go for it.
Okay, good. Oops. Okay, yeah. So let's talk about, what is a type? Well, that's kind of a loaded question, but a type is, it comes from logic originally. A type is, well, it's kind of a way of organizing similar things, right? But examples in programming are like, int, that's an integer type, double position floating point, blah, 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 blah. But more interestingly, you can do things like take structs. So you have a struct, let's call it S of int x, or maybe
yeah, like a vector 2, a vector 3, or
it's
like,
exactly,
or a transform,
a vector double XL. And so this is the same thing in type. So what does this mean? You can think of this as a product of double, right? This is the same thing as double cross double, right? So this is what's called a type form, or is this I shouldn't circle that, that's not good. Yeah, is this the product? You have product types. Similarly, you have things like you also have sum types, right? So sum types, I could have something like an enum, let's call it days of the week or something, and you either have Sunday, Monday, blah, 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 ... Okay, and so you could also write this as, an alternative notation. So it's one, the difference between product types and sum types is an element of the product type is, okay, so element of double cross double is an ordered pair. So let's say like 1, 2 is an example of something in here. But on the other hand, if you're an element of day is correspond to like a it's exactly one of the it's exactly, so you have Monday is one of the days. So the difference is this is what's called, this enum is another way of saying a sum type. So you could also write day.
So is this related to this distinction between parallel and sequential composition that you first talked about, like where types are tasks?
Yeah, for sure. So the parallel composition is clearly closer. So this is closer to the parallel composition idea. This is not exactly written explicitly in the paper, but because we're kind of doing a lot of like math to get stuff to work. But this is a lot closer than parallel. And so, sorry, let me just, you have Sunday plus, just to make it clear, Sunday plus Monday, blah, 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 blah. The sequential composition is a lot closer to this sum type idea. You think of like sequential composition. as like a union where you identify stuff in an overlapping mode, right? And so it's closer to the sum type idea. So that's a good thing to point out. Yeah. Okay, so these are kind of the most basic, what are called, oh my gosh, is there a better way? I need to, okay, so these are the basics of what are called algebraic data types.
Mm-hmm.
So why is it called that? Because you have like products and sums, right? And if I had, there's kind of these natural, isomorphisms. If I had something like, double, it's kind of a funny thing, but, if I had something like, bool times double plus double, well, guess what? That's the same thing. There's a what? So this funny symbol means there's a one-to-one correspondence, right, between that and well, okay, there's other stuff the funny symbol can mean, but let's just say, it's the same thing as bool. Sorry. Oops.
Like, yeah, but you can do algebra on the types as well.
You can do the algebra on the types, exactly. And this is like there's souped up versions of this stuff, but this is like the simplest case. Okay, so you can do algebra on the types. Okay, so what should I talk about? So so this is like the background of the whole type theory thing. One other thing I should mention is there's something called if you're interested in logic, right, there's something called the Curry-Howard correspondence, where you can, the same sort of structure behind manipulating types corresponds to logic in the following sense. You have your data types correspond to propositions in logic, and your terms of your type. So for example, a term just means an instance of the type. So true in bool, or 1.0 whatever in double, correspond to proofs of those propositions. So there's this if you talk to real type theorists, not people like me who are just mathematicians who are then this is their bread and butter type stuff. And by the way, you can, if you soup up algebraic data types to what are called dependent types, you can do all of mathematics using dependent types, right? And so using this way of doing proofs, so you can do proofs using a computer in like Coq or Idris or Agda, using these dependent types. Okay, but to get back to robotics, I guess, unless any questions, Mark?
No, this is super clear actually, and I think this was a great intro to type theory and like the basics of algebraic data types. I thought this was great.
Great, thanks. I should I've done this once before and it was interesting. It's always kind of, yeah, but I should get more practice doing this. Okay, so let's talk. So robotics. So let's say I want to okay, so let's give an explicit definition of a hybrid system. So I've been talking a little bit about hybrid systems using these examples and hand waving a little bit, but here's a real definition that's basically the same one in the paper. So a hybrid system, H, corresponds to a graph. Let's call it the graph. Let's call it G, maybe G of H if you want, but let's forget all the extra superscripts. And the vertices of G are called the modes. The edges are called resets. Okay, and what does that mean? That means for each vertex, for each
So let's say vertices V, edges E. For each vertex V and V, right, you have this dynamical system. We kind of, there's a bunch of extra data, but the main point is you have a flow set F where, okay, sorry, I forgot to define something. So we have this manifold MX is, excuse me, this continuous dynamical system corresponding to a manifold and a vector field. But there's also, we also have to talk about when you can, so the way we're setting things up is we want to be able to talk about sameness of hybrid systems, right? So like the basic, one of the basic things behind category theory is the idea of a morphism. So that means a structure preserving map. So for example, you know, if you're familiar with like group homomorphisms, you have to it's something that preserves the multiplication.
So for example, is the application here being able to figure out when are two different manifolds and vector fields actually equivalent? Is that the application in this case when you say morphism?
Yeah, well, yeah, that's I guess the classical example is something called conjugacy, semi-conjugacy, or conjugacy of dynamical systems. So yeah, maybe I'm just mentioning this as motivation, but why don't I just go back to that first? So let's talk a little bit about you know, semi-conjugacy. Okay, so semi-conjugacy, the intuition is that okay, so let's say I have a semi-conjugacy, oops, let's say phi, pardon my Greek, phi from a dynamical system mx to you know, ny. Okay, what does this mean? So the intuition is that the image, basically, if okay, in some sense, flowing in mx, or you know, applying the vector field is the same as flowing, let's say, from a point x in M, flowing from phi of x, so phi of x in N, so phi of x in N with respect to the y vector. Yeah. Okay, so
interesting. So and so when you say flowing, like, do you mean like if you were to just chart out the path of like an initial point x0, you're saying that like if I take x of 0 in the first vector field, it should follow the same path as phi of x in the second vector field.
Right. Well, if you apply phi, right? Yeah,
yes,
yeah.
If I apply phi.
Yeah. So one example, let's say I have a circle. This is like simplest possible vector field. You just have like theta dot equals 1 or something, and then I could embed it in the plane in your in a pendulum. So well, I guess this is kind of boring, but again, you could write it as theta dot equals 1, but if you wanted to change of coordinates would be kind of a trivial semi-conjugacy.
So actually, like, this does show up in so there was a textbook I had read a year ago called Modern Robotics, and they talk about this idea a lot of like, well, some representations will have singularities in them, so you map it to a different space where you won't have these singularities. But the treatment in the book is very topology heavy. But it seems like they're talking of a similar language as you are, which is like, well, I want to move it to another space it's more convenient to work with.
Yeah, that's great. Yeah, so what I'm doing, this is a smooth one, but you can do the same thing with topological semi-conjugacy. And so just to draw, since it's supposed to be a math or category theory talk, basically, if you the topological semi-conjugacy, you can let me just it's the same idea. It's a generalization of the smooth semi-conjugacy. And the way you write it is the following. So suppose I have a point x. So here we have phi from, let's say, m to n. In these, so there's some flow on it. But basically what it means is, let's say I apply, or actually, let me make this an alpha, sorry. So let's say this is defined by some flow map phi. Oh my gosh. So basically you have a flow map here. Let's call it phi from m cross r to m. So, and similarly there's maybe like a phi prime over here for n. So this just defines what happens. So here we have flows, which I haven't defined yet, but basically m cross r is just the time to m. So what that means is basically you start at a and I could write like phi t of x. So here this is the t coordinate. Phi t of x is the flow. So here I have some space. Here's x, and then if I flow for time t, then phi t of x is this point here. That's all. That's a way of describing a topological flow. And if you can draw a little commutative diagram, which is like, here's phi t. Let's say alpha is a semi-conjugacy from m to n, right? So here's alpha. Here's the same alpha. And let's say this is the flow. Maybe phi sub m is the flow on m, and you can do the same thing over n. So the main difference is you do it. So here, this, if you go this way, that means you flow first and then you apply the map that sends you to the other space. So and here you just apply the map in the other space. So this is like
wait. So is this like sort of I guess a rigorous way of saying that you can take any point along the path and go back and forth between the two representations?
Yeah. So
okay,
this is called the semi-conjugate. This is what it means to be a topological semi-conjugacy.
It's like the whole path is also semi-conjugate as opposed to a single point is semi-conjugate.
Right. Actually, in fact, this is true. If you start at any point in M, this is true. I mean, so if you go back to this picture, right, this whole path goes to this whole path over here. If you outside of this image of, maybe I'll call this alpha since I'm already so outside of this image, it could do whatever it wants, but inside the image it looks the same, right? There's some funny stuff. In this case, they're nothing's gets crunched up by the map, but yeah, this is the basic idea. There's some technical stuff that might not make it exactly this. There might be multiple copies in the domain, but that's the intuition. Is just this. These things get sent to, these trajectories get sent to the direct trajectories. Okay, so this is like one, if you want to do category theory, or even if you want, semi-conjugacy, if you want to do dynamical systems theory, semi-conjugacy is a very natural notion, and it's a natural notion of structure preserving map. And so one of the ideas of category theory is you want to look at these maps to kind of organize your spaces. And I guess the first application, right, or whenever you is talking about products, right? So, yeah, why don't I? Okay, this is not exactly what's in the paper, but I think it's an interesting application of why you would care about structure preserving maps. So let's talk about products and universal properties. So if you're given a category, so what's there are other ways? So suppose I have this Okay, so when you think about a product in what's called the category of sets, right? You just think about like A cross B. You just think about ordered pairs.
Mm-hmm.
So this is a product in sets. So let's just say sets. Okay. Now, what if you have a different category? How do you talk about products? Or for example, this this hybrid systems category. I guess that's a perfect example. So, oops. Oh my gosh. Done. Delete. Okay. So what about other categories? Let's try, graphs, hybrid systems, I don't know, groups, pick your rings, groups, stuff in math. Well, a lot of the times, this is good enough. You can just deal with ordered pairs. But for hybrid systems, which I unfortunately didn't get back to defining, there's a graph plus there's a bunch of extra data. How could you, talk about that stuff? And well, the way, a way that's worked for math, pure math at least, is by using what are called universal properties. So let me explain in sets what's going on. So, okay. Oh my gosh, I never defined categories. Okay, so let's draw some arrows and then we can fill in the details later. So here's a set. Let's think about these as sets first. But okay, so I want to say, how can I define A cross B? This is, the set of ordered pairs in terms of just arrows and like morphisms in the category. So in sets, it would be functions. In other categories, it could be what we just talked about, which were semi-conjugacies or, group homomorphism, what have you. Mm-hmm. Well, the way you do this is you talk about what's called a universal mapping property. So let me just draw the diagram first. Okay, so what does this mean? Okay, so this is some indecipherable, alien language apparently. But what this means, you're given two sets, A and B. These are the inputs, and I want to define this output, A cross B. And the way I'm defining it is the following. So given, hopefully I did the right way. Oh my gosh. No, I did it the wrong way. Sorry. Oh my gosh. A cross B should be here. And here's a C, and there's a universal map into it.
Yeah, so just looking at this, to me, like, if I remove the C part, this picture makes sense. It's like, oh, it's like a way of projecting or of picking the first or second element. Like, that's how I would understand those arrows. But then the C is, I think, the indecipherable part for me, at least.
Yeah. Okay, so let's yeah, that's exact. Okay, so let's start with. Let's start with just the projections. So let's say here, I want to say there exist these maps, these projection maps, and how do I know that it's like uniquely so the question is, how do I define this A cross B object without without saying in such a way that it's a unique object? And so for example, there's plenty of different objects I could say which you have maps. So for example, what's another object that has maps to both A and B? Let's say, I could do like, what's another, I mean, there's stupid things you can do, right? Like the point is this would be kind of an obvious construction. Like I could have like A cross B, union A cross B, right? And I just kind of do some stupid, always pick the first, I could say, so if I have a point, A, B, so let's things either look like A, B, or let's say an A tilde, B tilde, you know, I could say if it's an, well, I could just take some stupid union of stuff. But
well, I mean, like we can bring back the discussion to the sets and the hybrid graphs, like, because I think that's the interesting part. Is that like I think because like when I think of the discrete part of what you've described, as in like here's a state machine that's describing the transitions, that all makes sense. Then I think we started talking about like the dynamical systems in each of those nodes. But then transitioning between them, I thought was something that I didn't fully grasp. So maybe we can tie back.
Sure. Yeah. Let's go back. Let's go just so I don't leave it off on a bad note. What this means? So it's just some. Oh my. Okay. So let me just. Yeah, I feel bad about doing this, but it's just a way of defining. Defining it just in terms of defining the product just in terms of these maps so that it generalizes. And what this C means is that given any functions from C into, so if C into A and into B, then I get an automatic function into A cross B. That's all it says. Which means basically what you do is, well, what is this map, right? You just do well, okay, it's some God-given map apparently, but
but like I see, like let's say in this case, F would be like equivalent to, like, let's say the identity function from C to A times B, then composed with the projection function to get A out of A times B, and that's what F is. And similarly for G, it's the identity and then a projection from A times B to B.
Right. Well, that's if C is A cross B, but if C is some other random thing, right?
Oh, like absolutely anything. I see. Yeah. Okay, got it.
Right. And basically, what it should be. So what it should be is, what is this dotted map? The dotted map should correspond to just do F of. Suppose I take some element little c in C, then this C to A cross B. There's nothing really fancy about it. Just like F of C. In the sets case, right? So here's a sets example. F of C, F of G of C is the unique element. Yeah, I think probably this probably isn't.
No, but there's like an application here, as in like where is it easier for you to do your algebra? Is it at the level of A or is it at the level of C, for example? And like, let's say C is complicated, can you bring it back like down and do something else? So this is still, I think, like sensible. Like,
no, I mean, the thing is, I think it's not that complicated, but it's unmotivated because, well, I'll just tell you, the motivation is exactly to do the same things you would do with sets in different categories. That's it. But,
sure. Okay.
Yeah. It's kind of hard to do explain something technically without kind of getting to really examples. Anyway, so sorry, you were asking. So we were talking about semi-conjugacies, and then we kind of got sidetracked by products and universal properties because I wanted to give an example of why semi-conjugacies were useful. So that's probably the missing link. But yeah, so these semi-conjugacies are going to be some version. So this has to do with the smooth continuous part. But you can also soup it up to including the discrete stuff too. So then we have to talk about graph homomorphisms. So you have two parts. You have a graph homomorphism between the underlying graphs of the hybrid systems, and then you have these semi-conjugacies. And you can do that, and then you get products of hybrid systems in a way that you that's a useful independent. Suppose I have two hybrid systems defined by a bunch of nodes, right? So I have.
Wait, so I'm just finding it curious. You said two hybrid systems because my understanding is that a given robot corresponds to a single hybrid system.
Yeah. But let's say you have a hybrid system for, for a hopping one leg hopping, and you want to move your head, or so you have a hybrid system for locomotion. You have a hybrid system for head motion.
Okay.
And let's just say, for the sake of argument, that they're completely independent.
Great. Yeah, like you've programmed them independently, you've tested them out in whatever, like using Python code or C++, whatever they work. You have those two systems.
Yeah, and you want to stick them together,
Yeah.
right? And let's say there's stuff that, and you want to define a giant hybrid system that has both of them, and maybe you want to do something else with it, right? Maybe you want to talk about, there's some guard. Suppose there's some guard conditions that involve both, right? Let's say you want to do something whenever you want to jump or something, and you want to grab something with your head, whatever. And so what this product would do is tell you is tell you exactly what in a completely formal way, what is this hybrid system? What is a hybrid system? It's kind of the one way of knowing that it's quote unquote the right product is saying it satisfies this universal property with respect to the semi-conjugacies.
Oh, I see. Like you're basically formally proving that you can compose them independent. Like composing them independently is the same as just having done everything in a more monolithic way.
Yeah. I wouldn't say that this is a super application. I mean, it's just like a really simple thing that you can do to define products, which I guess is, I guess it's useful. I mean, I guess it's a useful basic idea before we get into, more complicated stuff. But
I actually don't think it's all that basic, like, because I mean it's not entirely trivial how you would do this with existing code, right? Like how you would just
sure, yeah. So yeah, exactly. So there's a bunch of other really cool stuff, but yeah, this is actually, I think you're right. It's kind of it would be a significantly useful thing, right? It would be a useful thing if, instead of doing everything using event loops, you program using the hybrid system C++ class, or your own C++. There's not that much to implement, and then you take products, and you still have a class. You still have something using this data type. You don't have to like do it. That's actually a good point. The engineers at the lab are typically doing this by hand. I mean, the thing is, it's sometimes there are some finicky stuff about not things being exactly independent, but you can often like add like a correction vector field. There's different things you can do to make it a little bit more useful. But maybe go ahead.
So I guess like a good segue into what we can talk about for the rest of the talk. I don't know how big of a question this is, so I'm just gonna ask it.
Sure.
Is that, like, let's say like a lot of times, like, I mean, like, I'm sure like people with your expertise like will have lots of domain knowledge as to how to construct these proofs and do all these diagrams. But like, let's say now if we want to bring it back to the practitioner, like, is there a sort of like language they can use to compose these stats? Like, what would their user experience look like?
Yeah. Okay, so well, the language is called C++ in ROS, but yeah. So that's the whole idea behind the type theory. Is right now we're defining the category, or we define a category which is potentially useful, and then to make it useful for people, right? You want a type theory for example, instead of talking about ints and doubles and structs, you'd like types of hybrid systems, right? Or type. Right.
Because when you're saying hybrid system, like in my head, I'm hearing like task or like part of a robot.
Right, types of behaviors, robotic behaviors.
Yes.
Right, exactly. And that's kind of that's kind of the hard thing, because you want it to be physically you want it to be useful. You want it to be physically grounded, right? You could easily define types which are just like, I don't know if you're familiar with like LTL or. So you can easily define types by like partitioning state spaces, right? You just partition state space and say, if you're in this room, for example, then you're blah. But what you'd really like is you'd like to have types which come from the underlying physics. Okay, and so we're working on that. But one way of doing that is what's called Conley theory. So there's a way of talking. So this is like after the paper, but there's a way of getting symbolic information. There's a way of getting topological information out of an arbitrary dynamical system by someone named Charles Conley. And using this, you can talk about what are called chain recurrent components. There's basically a generalization of recurrence that is stable with respect to perturbing your parameters. And so these are the kinds of things that we would like as types. But
that's interesting. Like let's say like when you're saying like, okay, so like let's say when I think of it, let's say I have a robot and it looks like some sort of humanoid. So there's a bunch of pendulums which correspond to the arms. There's some actually like it's just a bunch of pendulums attached to each other. They each have their own center of mass, their own length, their own maybe like even their own coordinate system. And so like let's say they're each independently achieving some behavior to achieve some goal, like reaching an apple, and I just want to compose all of these behaviors in one go to achieve some end level task. And so like let's say when you talk about Conley systems as well, like do you mind talking a bit more about how that relates to solving the problem of like composing tasks? Because I think
sure. Yeah. Okay, so actually, do you mind? That's kind of like pie in the sky stuff right now.
Sure. Okay,
so
let's bring it back.
Let's bring it. I mean, ideally, you would have like before I bring, let's bring it back. But ideally, the Conley theory would say, you have this topological type, maybe with some extra conditions that are non-topological, but you're in this, for example, limit cycle, right? What the Conley theory can say is that you're in this sort of it gives you topological information about some steady state behavior, meaning are you in a limit cycle or are you in a it's a generalization. You can talk about like generalization of the Morse index, right? So basically, suppose you're at an equilibrium point, how many eigenvalues are positive or negative, that kind of stuff, or what you have. So you have this kind of data, and you could say, well, if I use, I mean, the far away ideal would be to say, I can apply this controller if I'm in this kind of steady state, topologically speaking. But let's get back to the actual partition. So what I would say, if you want to get started on this,
actually, like, do you mind if I share my screen for 1 second? I want to show one quick thing, because what you're talking about reminds me of. Actually, no, sorry. Yeah, sorry. I'm just gonna show my webcam. So this is like from the Stephen Strogat's book, The Dynamical Systems, and I remember he had this like picture at the very beginning where he like talks about dynamical systems relative to n, whether it's linear or nonlinear. So he does this sort of like classification of systems. And so I guess like if you think of these as types, then they're figuring out how to compose them becomes interesting. This is a very bad picture, but I'll just find, like, I'm sure like Stephen has something on his Twitter or something. I'll share it with you later.
Cool. Yeah, I mean, what I'm just trying to say is like the holy grail of a lot of stuff, a lot of machine learning even would be synthesizing useful types, right?
Mm-hmm.
Right now, it's really hard to go from, to go to symbolics, right? Useful symbolics that have some underlying grounded meaning. And this Conley theory seems like, the maybe baby steps towards doing that.
Interesting.
Yeah. Actually, let me just I can just show you this one. Let me just show you one picture about that before I get off the subject, because it seems kind of. I haven't. We wrote a paper on this, but I think this stuff. This is not by us, but it's really interesting stuff. So it's by a group at Rutgers. His name's Konstantin Mishikow. Okay. And it's called computational. He does a lot of stuff with computational homology. He has some great students too, or I don't know, collaborators too, like Sean Harker, and someone named Kelly Mislov. But so the thing that I'm interested, one of the things that I think would be really cool is to do what it's called. They call it the Conley-Morse Database. And so what they do, let me share the screen.
Yeah.
Desktop. Okay, so here's the setup. What's it, spam log? Okay, so there's two things that I think are really this is not this, I don't think you can, he just uploaded this stuff and I don't think you can run it yourself, but they do a lot of really cool stuff involving you take in some dynamical system and then you can get out this recurrent data, recurrence, you know, kind of what is going on, this steady state recurrent stuff. How do I page down? Oh my gosh, Max. Oh my, okay. Apparently this is the. So basically, what they do is they grid up state space and parameter space, as a matter of fact, but grid up state space, and then they turn a dynamical system into, you know, a discrete thing. What happens to the grids? So basically, you transform your dynamical system into a graph where each grid element has an edge going to where it would go under the other grid elements that it could go to under the dynamical system under like one time step or something, and then you can get out this
Oh, it's like unrolling all possible histories of a progression of a system into a graph.
Kind of. So okay, so it's like this. So I don't know if they have a good picture. Actually, they probably have a great picture here. Where is there a method of doing this? Okay. Yeah. So oh yeah, here you go. So maybe this is what you're getting at. So here you have some dynamical system, or let's just say a map on some space. And here's a grid of the space, and this is where this box under this map F that defines your system, it gets smeared out over this region. And so what they do is they say, okay, we don't know, you know, where a particular, but we don't know exactly where a point in here would go, but we do know it would definitely go inside one of these boxes. Right? These boxes cover the smeared out thing. And then you say, okay, the directed graph for this vertex, you have to have, so the edges of the graph isn't shown here. The graph the graph has vertices that correspond to every single square. But this would, right.
And similarly, like once you're at one of those projected points, you project into another graph. And that's what I mean by all the history. It's like you have a graph.
That's exactly right. All possible histories. That's exactly, or maybe future. I don't know. But their future history. I don't know. But yeah. So it gets pretty bad. It can get really bad, right? Because you're kind of exploding.
It's massive, yeah.
Yeah. But apparently they can run it on some, you know, some like they do some stuff with like some genes or something, some like gene expression regulation stuff. But this is but what I was, as far as the, and once you get this graph, right, that's kind of this combinatorial approximation, then you can find like strongly connected components, for example, and you can apply just graph algorithms. And it turns out their theorems say that these, if you go back from the graph, you calculate these components in the graph, you go back to the original system, then they give you guarantees about your original system too, which is really cool. And you can still, even better, since it's all this Conley stuff, is all this stuff, you know, if you vary the parameters, then the Conley theoretic data, whatever, you know, these kind of qualitative kind of big picture features are vary continuously. And so you can kind of get these phase diagrams with respect to the parameters. And I think they have it here. Okay, yeah, I think this is exactly it. So here's one example of, they call it, there's this Leslie model. It's some famous, you know, you have some famous map, right? This is some map on R2. And then, you know, for some parameters, you can, here's what the, this is what the Morse component, whatever, these are like the steady state things, these different colored little pieces. And then in between these, in the white and the gray area, everything is gradient like. It's basically, so the big Conley theorem says that everything in a dynamical system, you can break it up into the chain recurrent part, which is basically kind of steady state recurrent stuff that's going on. but it can get wild. And then there's a gradient-like part, which is basically like flowing down a hill. And so this is kind of, and then you can, so you get these different like steady state pieces and stuff that's flowing down the hills. And then what they can do next, which is really cool, is then they can even do like a little parameter space phase diagram. So each one of these points in parameter space corresponds to a dynamical system with its own graph and everything like that. And you can see like what happens as you vary the parameters. How does this Conley-Morse how does this stuff vary? So
I mean, yeah, like this is very cool because I think for me there's sort of two interesting ideas here. One is that it takes something which doesn't look tractable and turns it into something tractable. And the other is it makes something very complex into a sort of interactive visualization so you can better understand it. And I think in of themselves, those are both huge benefits. And it's like something I've thought a lot about because, like, let's say in reinforcement learning, for example, like typically, like, let's say you've trained something to solve some task and, you want to start composing it, but it's trained on two different tasks. Like composing it isn't easy. There's no UI for it really. It's just, you have to hook stuff up in a command line interface and you have to hope everyone wrote their code in such a way to make your job easy, or you have to write the interfaces yourself. So this is very exciting. I'm definitely gonna read this paper, I think, after this, like after we're done here. But yeah, thanks a lot for sharing.
Yeah. Well, and just to get back to the type stuff is, for example, you could say, this would be this color on this thing, meaning that all the corresponding systems have a similar kind of qualitatively similar behavior would be an example of a type that is coming from, a type you could label it, right? So this is the kind of really interesting stuff that could happen. But what am I trying to?
This is so I was thinking, Paul, like maybe because the talk would be long. So if you like, is there like sort of some recurring points or summary you'd like people to really get out of this? Like if like let's say you're someone who's a bit interested in robotics, a bit interested in category theory, you never dive too deep. What are the main points you want people to remember by the end of this talk?
Yeah. Well, oh man, I would say if playing okay, so if you're just some person who's like vaguely interested in categories, I would say getting in playing around with Haskell is probably the easiest way to do useful stuff with it. Although hopefully I'll at some point I'll show you guys I'll be out with what I call Lemberry, which is this collaborative way of doing functional programming using an IRC bot or whatever. It works with Haskell right now. But if you want, just try to use, if you're programming a robot, for example, I would say it's a good idea to use a hybrid system data type. That's maybe the bottom, the simplest thing you can do is use a hybrid system, not necessarily this, but write your own if you want. Instead of writing an event loop with a bunch of modes, because then there is a potential to make it more modular using a data type rather than doing everything very imperatively. Those are the two main takeaways.
It's interesting, like so I guess it's very interesting to me, like just the breadth of topics that you covered, and actually, like you remind me of one thing. I just want to briefly talk. We may just make the talk longer, but so in Unity, for example, or game engines, there's sort of two main programming patterns for games. Like one is the event loop, which is what you described. But then there's another one called the entity component system. And the way that works is that you assume that each entity in a game is a server, and it can send events to other servers, like other entities. And then based on receiving those events, it triggers some behavior on it. The nice thing about it is that there's no such thing as, there's no synchronization. Like each of these things is completely independent. It's doing its own thing. And it's actually the only pattern now that lets you make games that scale to tens of thousands or millions of entities on screen. So for me, once I learned that in game engine development, it was almost impossible to unsee. And I think it touches upon a lot of the ideas that you also talked about.
Yeah, well, I think in ROS too, right? I mean, they have this message passing interface. Yeah, that seems like it could potentially be related. I don't know, and I mean, there's a bunch of like multi-agent stuff that's hot among certain people. I don't know. I mean, that's an interesting thing to think about. Yeah, the whole multi-entity thing. Yeah.
Well, thank you, Paul. I think you definitely made me think about like so much stuff. So I'm super grateful that you spent the time talking
Sorry,
with me.
it was so broad. There's too much.
No, on the
Yeah.
contrary, like I the opposite. I felt like I learned so much, and I think once you have like your second paper, like I'd love to have like a second chat with you because I feel like I learned so much. So thank you so much, Paul. I really
Thank you, Mark. Yeah, it was a lot of fun.